We're on lesson 6 of calculus using a textbook of Larson. We're on 1.3, finding limits analytically. So we, in lesson 5, found limits looking at the graph and by looking at a chart at the numbers as the numbers came closer and closer to being to that value of x, what the y values were getting closer to. You can also, what we're going to do today is learn how to recognize which limits can be evaluated by direct substitution. When the limit of f of x approaches x, as x cannot be evaluated by direct substitution, try to find a function g that agrees with f for all x other than x equals c. Then apply theorem 1.7 to conclude analytically that the limit as x approaches c of f of x equals the limit as x approaches c of g of x, which is equal to g of c. Or we can always use a graph or a table to reinforce your conclusion, which was what we did yesterday. So all of these on this page, you can just plug the number in, because when you plug the number in, it's not undefined. The graphs that we looked at in the last lesson, when you plugged them in, you were dividing by the number 0, or some other thing happened, and so when you plug it in, it's undefined. Today, if you plug in the number 3 on the denominator, you get 5. That's not undefined. That doesn't make 0. So if you just plug in the number 3, you get the square root of 9 over 3 plus 2, 5. So you get 3/5. The next one here, f of x is x plus 7, and g of x is x squared. Neither one of those are undefined at any of the numbers. You can plug in, both of them have an infinite domain. Both of them have a domain from negative infinity to infinity. And so you can plug in any number you want for x. So when you plug in the number -3 for f of x. So f of x was x plus 7. So when you plug in -3, you get -3 plus 7, which is 4. For g of x, it's x squared. So plugging in the number 4, you get 4 squared, 16. All right, g of f of x. Well, we had just found f of x as it approached -3. So as it approaches -3, we got 4. So that is equal then to the limit as x approaches -3 of g of 4. So then g of 4, putting the 4 in for g, we already did that, and we got 16. All right, so remember when you're doing g of f, you have to start with the inside nest and plug it into the one that's to the left. Okay, cosine has an infinite domain from negative infinity to infinity. It is defined for all x. It's a continuous sine wave, sine cosine wave. So anyway, when you plug the pi in, you get the limit as x approaches pi of the cosine of 3 pi. Remember, cosine repeats every 2 pi, so we can we can take off 2 pi from it. So it's really the limit as x approaches pi of the cosine of pi. 3 pi minus 2 pi is 1 pi. And so hopefully, again, you're remembering what it looks like visually in your head. It starts and ends at 1. In the middle at pi, it's down at -1. Then it goes through zeros. So when it's pi, it's down here at -1. All right. Sometimes, though, it's going to be undefined. And when it's undefined, we're allowed to divide out where it's undefined at and then continue on from there. So it's called a dividing out technique. So let's do that on one of them here. Now, if we plug 5 into this, it's going to be undefined because you'd have 5 squared minus 25 or 25 minus 25, which is 0. So you can't do that. But we can factor in the top and the bottom. The bottom factors into x plus 5 times x minus 5, and the top, if you take out a -1, it factors into an x minus 5. So we can cancel out the x minus 5, which leaves -1 over x plus 5. That's called the dividing out technique. Now, when you approach the number 5, when you put the 5 in there, you get -1 over 10. So it approaches the number -1/10. Same thing on next one, on number 52. We can factor that. So the top of it factors into, let's see here. I don't see it. That's okay, I can do it myself. So the top of it factors into, let's see, x and x, 4 and 2. We want it to be a positive 2, so it's plus 2 and minus 2. And on the bottom, 2 times 1. We want it to add up to a negative 1, so we want the 2 negative and that one positive. So the x minus 2 cancels out, which is good. So that leaves you with x plus 4 over x plus 1. So when you substitute in then x equals 2, it gives you 6 over 3, or 2. And then sometimes you have a real mess, and so what you can do is rationalize it by multiplying the top and bottom by the conjugate of it. So here you got the square root of x plus 4, so the conjugate of it, remember you use the opposite sign, so instead of plus, you're going to multiply by the square root of x minus 4 on it. That's what the conjugate of it is. Or if it would have been minus, you would multiply by a positive 4. So, well, it's called rationalizing. All right, so by multiplying by the conjugate. All right, so down here, we're going to rationalize it. If you plugged in the number 3, you'd have 3 minus 0, undefined. So you can't just plug it in. So what we're going to do is rationalize it by multiplying by the conjugate. It's minus, so we're going to multiply by the opposite, plus, on the top and the bottom. So it's like you haven't done anything because you're multiplying the top and bottom by the same fraction. So it's not a big deal. So on the top, you're multiplying the whole thing by it. So square root of x times plus 1 times the square root of x plus 1 is x plus 1. And then the middle here you have negative 2 times the square root of x plus 1. And on the outer you have 2 times plus 2 times the square root of x plus 1. And then negative 2 times positive 2 is negative 4. And then in the denominator, let's start with the x. So x times the square root of x plus 1, then x times plus 2. Then on the inside you have minus 3 times the square root of x plus 1, and then minus 3 times plus 2 minus 6. All right, so from doing all that, it cleans up. That's gone because it's minus and plus. So on the top, you're left with x minus 3. And then down in the bottom in the denominator, what you're left with, you know what? I think we probably should have just left it alone. Yeah, if we would have just left it alone, we have x minus 3 times that whole chunk there, the square root of x plus 1 plus 2. We didn't need to do all that. So that's gone. And then you're left with 1 over the square root of x plus 1 plus 2. All right, so I overachieved on that. I'm sorry. Okay, so we're still trying to find the limit, though, as x approaches 3. So now that we've rationalized it, you can just plug the 3 in. So the limit as x approaches 3 is 1 over the square root of 4 plus 2. So it's 1 over, let's see, square root of 4 is 2 plus 2 is 4. So you get 1/4. All right, next one, same idea. You're going to multiply by the conjugate. So instead of minus, I'm going to multiply by a plus. So the square root of 2 plus x plus the square root of 2 over the square root of 2 plus x plus the square root of 2. All right, so on the top, square root of 2 plus x times the square root of 2 plus x is just 2 plus x. And then the square root of 2 plus x times the square root of 2 would be plus the square root of 2 times the square root of 2 plus x. Now do the negative 2. So negative 2 times it is minus the square root of 2 times the square root of 2 plus x. And then negative square root of 2 times positive square root of 2 is negative square root of 4. And then on the bottom, I'm just going to leave that alone. I forgot to leave it alone. Sorry about that. Okay, so on the top, that's gone. And you have x, and that square root of 4 is 2. And so you have minus 2 plus 2, they're gone. So you have just the letter x left on the top. Over on the bottom, x times, in the chunk here, square root of 2 plus x plus the square root of 2. So you can cancel that out. Now you be careful. When you cancel the x out here, you have to leave the number 1 on top, because this is in the denominator. It's going to stay in the denominator. It doesn't float up magically because you've canceled out the letter x's. It stays in the denominator. So we're finding the limit again as x approaches 0 of all of this. So now we can just plug in, oh, I made a mess there, didn't I? Now we can just plug the 0 in. So that gives you 1 over the square root of 2 plus the square root of 2. So when you do that, you end up with square root of 2, one of them, and plus another one of them. You get 1 over 2 times the square root of 2. So that's the answer. And then there's a couple special trigonometric values that you need to memorize. So make yourself a flashcard. The limit as x approaches 0 of the sine of x over x equals 1 all the time. And the limit as x approaches 0 of 1 minus the cosine of x over x equals 0. You need to know those. Then what you can do on those is you can clean them up to make them, when you have trig functions involving that kind of, when it looks a little like it, what you do is to clean it up and make it look like it. So the first one's really quick to make look like this one. The only difference between this and this is the number 3. So just pull the number 3 out in front, which you're allowed to do. So it ends up with 1 minus the cosine of x over x as the limit approaches 0. And by the theorem up here, theorem 1.9, that equals 0. So it's 3 times 0 or 0. And then the next one here, so we kind of have it here. We got tangent. Remember, tangent is sine over cosine. So on the top, we have cosine times sine theta over cosine theta. And that's cosine over 1. So that's the top, cosine times that, and the whole thing's over theta. Oops, let me move it up. So we got cosine times tangent, which is sine over cosine, over theta. So that's gone. And then that's just the sine of theta over theta, which was the very first one. The limit is x approaches the sine of x over x. And they just changed the letter x to the letter theta, the Greek letter theta. So that is the limit approaches 0 is equal to, the theorem says 1. Because that's what the theorem says right here. All right, so that was lesson 2 of calculus. But yeah, we'll see you for the next one.